Carbonyl cyanide p-trifluoromethoxyphenylhydrazone is a weak lipophilic acid which acts as something known as an ionophore, specifically a protonophore, which means that it is able to situate itself within biological membranes and essentially facilitate the movement of protons across the membrane. So how this impacts cellular respiration is it causes something known as mitochondrial uncoupling. So mitochondrial uncoupling is this process where it results in this dissociation between the actual formation of an electrochemical gradient, in this case between the intermembrane space and the mitochondrial matrix, and the use of that electrochemical gradient to actually produce ATP through chemiosmosis and ATP synthase. So what will happen in a healthy cell is you will have electron carriers in their reduced state, and these electron carriers are going to drop off each 2 electrons into the electron transport chain. They're going to pass through 3 enzymes, NADH dehydrogenase, the BC1 complex, and cytochrome oxidase complex. And what they're going to do while they're there is they're going to temporarily provide the energy for these enzymes to pump hydrogen protons across the membrane against their concentration gradient from the matrix into the intermembrane space. And this is going to result in an increase of hydrogen protons in the intermembrane space, and they're going to remain trapped here. And what's going to happen is this is going to form an electrochemical gradient, chemical because there is more hydrogen, and the electric part comes from the comparatively positive nature of this space compared to the matrix. And what these are going to want to do now is move down their electrochemical gradient by chemiosmosis. So they're going to be forced to move through ATP synthase, which is this enzyme right here. And what they're going to do is they're going to exert something known as proton motive force on this enzyme, essentially turning it and facilitating the oxidative phosphorylation of ADP and inorganic phosphate into ATP, which will result in a net yield of 32 ATP from the electron transport chain. So the way that FCCP plays into this is that FCCP is essentially able to provide these hydrogen protons another means of exiting the membrane or the intermembrane space without actually having to pass through ATP synthase. So what happens is you end up with less proton motive force exerted on ATP synthase, a more shallow electrochemical gradient, and ultimately less ATP being created. So this is also going to have an impact on glycolysis. So what you have over here is the third step of glycolysis right here. This is one of the main regulatory steps in respiration, as it is one of the first portions that is not readily reversible. So what's happening here is the conversion of fructose 6-phosphate into fructose 1,6-bisphosphate, and this conversion is catalyzed by the enzyme phosphofructokinase, which is regulated through something known as negative feedback inhibition, where the product of one of the products essentially that the enzymatic catalysis leads to is actually going to be used in order to inhibit the enzyme in order to regulate the amount of product that's produced. So the substrates for phosphofructokinase are fructose 6-phosphate and ATP, specifically magnesium ATP. And what these are going to do is they're going to bind to the active site of this enzyme. And the reaction is going to take place as per normal. What happens in the presence of FCCP is that the body becomes starved, or the cell becomes starved for ATP. So it's going to try to gain ATP in whatever way possible. There's going to be a lot more ADP in the cell because the ADP isn't being phosphorylated through oxidative phosphorylation into ATP. You've really only got these ATP being produced through substrate level phosphorylation and glycolysis in the Krebs cycle. So what the cell is going to try to do is it's going to try to take ADP plus ADP, and it's going to try to turn them into ATP and this thing called AMP, adenosine monophosphate, which acts as an allosteric activator for the enzyme phosphofructokinase. So it's going to bind to the allosteric site of the enzyme, and it's going to increase its affinity for its substrates and increase its rate of reaction. You're going to have more fructose 1,6-bisphosphate, and you're going to have more pyruvate ultimately going into the Krebs cycle. The Krebs cycle goes relatively unaffected. It is this essentially a process that reduces various electron carriers and also produces energy through the oxidation of this thing right over here known as acetyl-CoA. And by the end of the Krebs cycle, per each glucose, you'll have 2 pyruvate. So this only shows 1 turn of the Krebs cycle, but normally you will have 2. So per each 2 turns of the Krebs cycle, you're going to have 8 NADH and 2 FADH2. And this additional 2 FADH2, which I have shown here, is essentially coming from the electrons which are dropped off from the NADH used in glycolysis into FAD into the mitochondrial matrix so that these NAD and can stay inside the cytoplasm and continue to facilitate or continue to accept electrons in glycolysis. So what happens here is these are going to continue to move into the electron transport chain as per normal, 16 electrons from NADH, 8 from FADH2, and this is all going to happen as normal. The only issue is the fact that the efforts are ultimately futile, as this electron, the electrochemical gradient is essentially going to just be dissipated due to the presence of FCCP. So how does this impact the organism as a whole? Well, ATP is vital to the survival of any organism. The ATP is important for cell tissues to survive. So what's going to happen is cell tissues are rapidly going to die, and specifically, this might cause issues with muscle contraction. So one of the important muscles in the body is the heart. And essentially, muscles contract through this method known as the sliding filament mechanism. And as you can see here, you have myosin, you have actin. Myosin binds to actin and causes it to move in this movement known as a power stroke. So what essentially happens is that this cannot occur in absence of ATP. So without ATP, an individual affected by FCCP poisoning is likely going to die of heart failure.